Welcome everyone. This is TW301 Basic Electronics, and in this lecture we will discuss the diode equation and the modeling of diode. And we will also try to understand why the modeling of diode is required. Why can't we use the diode equation for the purpose of circuit analysis? And there are certain limitations that we cannot use the diode equation the Shockley equation of diode for the purpose of conventional circuit analysis, and that is why we need to do the modeling. So we will try to understand these two topics in this small session. Okay, so let's start. So in the previous lecture we discussed about the forward bias, reverse bias of the diode, PN junction for the PN junction diode, and now we will discuss about the diode equation. In the previous class, we learned the characteristics of the PN junction diode, which is like this. This is the IV characteristics. Here, the current is in milliampere. Here, the current is in microampere. And characteristics of diode goes like this. So basically, this is the forward bias, this is the reverse bias, and here you can see this is the breakdown region. So the diode characteristics constitutes of three parts: forward bias, reverse bias, and breakdown. And we discussed about all these characteristics in the previous class. How can we obtain this forward bias characteristics when we are applying the positive terminal at the P side and negative terminal at the N side, and the reverse bias characteristics when the polarity of is reverse and the N type is connected to the positive and the P type is connected to the negative, and the P type is connected to the negative, and in that scenario the current is very less, and that current is equal to the I drift current we discussed in the previous class. And in the forward bias the diffusion current flows because the barrier is broken, and in the breakdown and if we are keep on increasing the reverse bias voltage, then at a certain voltage or at some threshold voltage, which is known as the knee voltage, there is a breakdown phenomena. And in the previous session we discussed about the this breakdown phenomena in brief and how the breakdown occurs. And now and the detailed discussion of the breakdown we will discuss in the subsequent session when we will discuss the avalanche and Zener breakdown, when we will discuss the Zener diode and avalanche and Zener breakdown. Okay, so here this characteristics of the diode is governed by the equation which is called the Shockley equation. So what is the Shockley equation? Okay, let me write the Shockley equation here. So the Shockley equation is like this: ID equal to I naught e raised to the power q Vd over eta Vt minus 1. So this is the Shockley equation which governs the behavior of diode. This characteristics is governed by this equation. So we will check this equation whether what we are stating here is true or not. Okay, with the help of analysis, we can check whatever I am saying, that this characteristics of the diode is given by this equation: ID equal to I naught e raised to the power q Vd over eta Vt minus 1. And in the previous lecture, I have already told you that there is a derivation for this equation which is not in our syllabus, and this equation can be obtained by the equilibrium condition that we have learned in the PN junction at the equilibrium. Okay, so here we will understand the terms in this equation one by one. ID is the diode current. ID is the diode current, or you can say the current flowing in the forward wise direction of the diode. And I naught is the reverse saturation current. We have discussed this reverse saturation current in the previous lecture when we were discussing the reverse bias. The current, the drift current that flows in the reverse biasing is also called the reverse saturation current. And this Q is the charge on mobile carrier, and basically electron. We know that electron or hole, the charge is same. The charge is 1.6 into 10 raised to the power minus 19 coulomb. And Vd is the voltage across the diode. Voltage across the PN junction diode. And this Vt is the thermal voltage. Okay, this Vt is the thermal voltage. Well, let me correct this equation. There is a problem with this equation. Actually, this Q will not be here. Vt. If this Vd over eta k, this eta Vt. So this will be the equation. Okay, this is the correct equation. Vd over eta Vt. Okay, this is the right equation. Vd over eta Vt. Vt the thermal voltage, and what is thermal voltage? What is the thermal voltage? Vt equal to Kt over Q. Actually, when we will put this Vt here, then you will get some Q and Kt in the denominator. But this is the thermal voltage, Kt over Q. And what is K here? Boltzmann constant. And what is T? Absolute temperature. And Q is the charge. Okay, so this is the Shockley equation which gives the diode current. Now we will try to analyze this equation, and we will try to find the currents at different voltages, and then we will try to find that what is the then we will try to find that that whether this equation is governing this this characteristics or not. So we will try to find out the characteristics with the help of this equation. Okay, one term is remaining, eta. Eta is the ideality factor. Ideality factor, which is one for most common diodes like germanium, silicon, and two for other kind of semiconductor material. But for our purposes, this we will take this one, unless otherwise given in the situation, unless otherwise it is given in the numerical. If in the numerical it is given as some value 1 to 1.5, then you will have to take that value. Otherwise, you will assume it. If it is not given, for all our purposes, we will assume it as 1. Okay, so this is the diode equation, and now we will try to analyze this equation. So one thing you can see, this is a non-linear equation. Here you can see the non-linearity is here, and this is a non-linear equation. We know that the exponential term is here in the equation, and this Vt. So if I substitute the value of this Vd in the equation, and then this equation will become, and if I put eta equal to 1, because I have already stated that eta is 1 for all our purposes, then this Vd over Vt is Kt over Q, and this Q will be here, minus 1. So this equation becomes like this. Okay, and if we try to calculate this term Q over Kt, if we try to calculate this term Q over Kt, and at a temperature of 27 degrees Celsius, then this will become 300 Kelvin. So at 300 Kelvin, this Q by Kt is approximately equal to 40. This Q by Kt is approximately equal to 40, and definitely the unit of this Q by Kt will be voltage inverse, because we know that Vt is a thermal voltage, which is Kt upon Q. So then the unit of Kt upon Q is volt, because it is a voltage, and the unit of Q by Kt will be voltage inverse. Okay, volt inverse. Okay, so this is the value at the 27 degrees Celsius, and now we will put this value here. Then this equation become like this: ID equal to I naught e raised to the power Q upon Kt is 40 times Vd minus 1. So now we have simplified our equation. Because thermal voltage, there is a thermal voltage Vt here, and actually there are many theories. I think you have heard about the Seebeck effect, Peltier effect. So there are various effects are there, physical effects, which governs the thermal voltages. Okay, so we need not to go in the physics of that thermal voltage. All we need to, as I already told you, the derivation is not in our syllabus. Okay, so if it is required, if you want to learn about this thermal voltage more, then definitely you can explore on the Wikipedia. But right now, this is a constant for us. Okay, for a constant temperature, this is just a constant. We will treat it as a constant because this is a Boltzmann constant. It has a fixed value, and this is the charge of electron. It is also has a fixed value. Okay, and the T will vary, and as I already told you that whatever we will perform on a constant temperature. So here we have chosen the 27 degrees Celsius, an average. You can see this is an average value. In winters, the temperature goes like 14, 10, 4, and in summers the temperature 44. So it is a average kind of average value. So you can treat it as a normal temperature, NTP. Even at the NTP is also called 24-25 degrees Celsius. Okay, so normal temperature and pressure, and this you might have learned in the physics. So T equal to 273 plus 27 degrees Celsius at 300 Kelvin. We have calculated the value of Q by Kt